Good morning, gentlemen, and Assalamu alaikum. My name is Mohammad Khurshid Alam, Assistant Professor, Department of Electrical and Electronics Engineering, American International University, Bangladesh, also doing PhD in University Malaysia, Pahang. Today's topic, study on critically minimizing cost in power systems with optimal design of stochastic wind power generators using Moth Flow Optimizations. Next 10 minutes and so, I'll cover the following. Problem formulations for optimal power flow and GW, MFO for single objective and multi-objective optimizations, Gray-Wolf algorithms, application study, recommendations, future works, conclusions, and finally question and answer session. The power grid, one of the most crucial components of smart cities, faces significant challenges in operating efficiently, dependability, and economically. One of these challenges is forecasting the demand for electricity. Grid managers can balance supply and demand properly while also minimizing operating expense for generating and transmission power. Thanks to accurate forecast, while maintaining respectable systems performance in terms of the limitations on the actual and reactive power output of the generator, bus voltage, shunt capacitors and reactors, transformer tap settings, and transmission line power flow. For a sustainable future and to meet the higher carbon emissions standards that are being put in place, it is expected that the renewable energy sector will experience enormous development. The current study using MFO determines a cost of $3,160 per hour for minimizing the cost of multiple fuels, which turns out to be the best price when compared to the legitimate results obtained by other algorithms. It results in a cost savings of 1.45% per hour when compared to the worst alternative results given by the comparison algorithms. According to simulation results on the IEEE bus network with 6 generators, these approaches might offer the best solutions right away. A further study found that this method works best for medium-scale power installations. The goal of this paper is following: development of a Moth Flow Optimizations algorithms to address the OPF problems. Number 2, incorporating the MFO into the IEEE 30 bus systems while taking wind stochastic integrations into account. Conducting statistical and comparative studies on Gray-Wolf optimizations and MFO in optimal power flow solutions. Considering cost-cutting measures for MFO and GW. Moths are actual search agents that move around the search area, as we can see in the figure 1. But up to this point, they have learned that flames are the best place to be. To put it another way, as shown in figure 2, flames are like to be flags or fins that moths leave behind while looking for food. Each moth is given a different flames to prevent local optimum stagnations. Moth can only fly toward a flame, not away from it. Therefore, if all of them are lured to one flame in the search space, they will all converge there. On the other hand, allowing them to pass through other flames encourages greater search space explorations and lessen the possibility of localization optimum stagnations. Problem formulations for MFO and GW. Here the ballpoint loading effect on a quantity cost functions, where K is a constant used to determine the shape of the log normally spiral. X is a random value between the 1 and -1, and di is the distance between the IM moth and di moth. Taking these factors into account, we propose the logarithmic MFO algorithm spiral as follows. That is function of x in between x square plus x if x is within 0 and 1. The Weyl probability density functions, that is PDF, as used is to mimic wind distributions, whereas a log normal PDF as shown the solar irradiations. The generating quantity cost as in shown in figure is being reduced, and the influence of the reserved modifications of optimal scheduling and penalty fees is being investigated. Gray wolves are a well-known predator in the wild. Gray wolf usually lives in a pack with a group size of 5 to 12 people on average. These wolves follow strict norms in their social dominating order, that is alpha, beta, omega, and delta wolves are among the gray wolves as we can see in the figure. The alpha wolf is the pack's leader and oversees making decisions regarding hunting and other activities, while the beta wolves assist a higher level wolf in making a choice. Omega wolves are the source of informing the top ranks of any informations. Delta results to all other wolves in a pack. Results in IEEE bus systems, test system. Table lists the lowest, greatest average and standard deviations of the cost imposed by MFO and GW in that order. Based on 30 simulation runs, as shown in the table, MFO outperformed GW in all statistical analyses. That is, the minimum is 19.68, whereas for GW the value is 20.04. The difference in results between the MFO and the GW is $0.36 per hour, which is extremely sustainable. If we multiply it by 8760, then it is coming as 3,160 cost savings each year for a total of 30 runs. The distribution result provided by all approaches were visually evaluated. Figure depicts the convergence curve for all strategies utilized to tackle these problems. Notably, the algorithms reach a point of convergence with 2000 iterations. The voltage profile may all the proven to be between 1.05 and 0.98 per unit of all load buses. About the future work, the optimal contributions of clean energy sources raised when a carbon price is introduced in a case study. The MFO has far-reaching consequences for future empirical research on creativity as well as for the notions of creativity itself. The technique keeps the best flame solutions identified so far and gradually exploits regions with good solutions. Adaptability, changing the number of flames, enables the explorations and exploitations trade-off to be balanced. Now about the conclusion, this research describes how to solve an optimal power flow problem while pursuing economic objective using the two evolutionary algorithm, that is MFO and GW. It results in a cost savings of 1.45 per hour when compared to the worst alternative given by the comparison algorithms. This method would be especially helpful for power planners and the operators who are interested in the power system's environment impact in addition to its cost. The IEEE bus systems with 6 generator units was utilized as a study sample. According to the simulation results, the MFO based on real code may deliver the greatest outcomes for the medium scale systems in a shortened amount of time. Now about the question and answer session. If you have any question, you can ask me.